All right, I think we're ready. Miles, you ready?
Yeah, I'm just making a link so it's easier to copy, so you don't have to type out that whole thing. One sec. Cool. Okay. Okay. Yeah, I'm ready.
All right, then I think we can start with the hands-on session of my lecture. So yeah, please take it away. Again, if there are questions here in the audience, we'll let you know. And yeah, please.
Cool. Okay. All right. Oh yeah, and do you think, is there any like camera that can see the audience? It's okay if there's no camera though.
I mean, Ranit, if you switch on yours, then I see a little bit of the audience.
Okay,
Yeah,
that's good.
I have mine turned around that I see people raise their hand.
I want to see like if everybody's like like they can't get something to work. Yeah. Okay.
They all left.
Went
for drinks, so nobody's here, you know.
Okay. Yeah, so thanks for coming. Today's my hands-on tutorial. There's a lot of stuff in this notebook, so I don't think we'll get to everything, but that's okay. So this is Google Colab. I'm sure many of you have used it before. It's basically like Jupyter notebooks for Google Drive, or like Google Docs. It's like Google Docs for Jupyter. It's really nice for this kind of setting because they have this like built-in Jupyter environment. They have GPUs available. So it's good for stuff like this. So if everybody could open this up and go to this URL, I'm going to zoom in, bit.ly/interpretml. And you should be able to get access to it. But let me know otherwise. So yeah, so feel free to go at your own pace. I'm gonna talk through the notebook a bit. So the brief summary of this notebook is that first we're gonna talk about PySer itself. So symbolic regression with PySer. We're gonna go through a few different examples. Towards the end, we're going to look at using PySer for interpreting a black box neural network. And then the last section, if we have time, I don't know if we will, but if we do have time, we're going to do some like Hamiltonian neural networks and different symmetries. Okay, cool. So hopefully you've opened the URL. Now, the first thing you want to do is make a copy of the notebook. So you go to File, Save a Copy in Drive. And that's just going to let you make local modifications and notes. So the next thing you want to do before you start it is you go to Edit, Edit, Notebook Settings, and then the Hardware Accelerator. You want to set that to GPU. Now they do have a TPU option, but for now we're just going to do GPU. I don't know what GPUs you have. I think I pay like $10 and I get this one. But the free one is probably fine. Okay, and I'm gonna just disconnect, delete so that you can follow along with me because I think I already ran this notebook. Okay, so once that's done, we're just gonna click the play button on the first cell, and that's just gonna start it up. And okay, so we're good. So now just follow these instructions, basically execute the cells, and this is going to install Julia and other packages that are required for PySer. If your Colab runtime, for whatever reasons, crashes or gets reset, just repeat the step 3 and 4. You might have to repeat step 2, but probably not. Okay. So this first cell is just going to install Julia, the Julia language. So this is what the backend of Python is written in. But Python is like a regular Python library. It's basically, instead of writing it in C++, I just wrote it in Julia and then linked it to Python. Okay, so that's going to go through all this stuff. It's going to start building the different libraries. So PyCall is kind of how you communicate between Python and Julia. That's going to take maybe a few minutes. So I think while that's going, we could, oh no, it's done. Okay. I think, oh yeah, the third cell is going to take a few minutes. So you can click on this cell. This is going to install Python and not PyTorch acceleration, not PyTorch Lightning. I lied. This is actually Hugging Face Accelerate. So this is Hugging Face Accelerate is basically just, it's a library to make deep learning easier. Okay, so when that installs, we're going to run this command, Python m Python install. This is going to install all of the Julia libraries for Python. This could take, I don't know, maybe 2 minutes or so. So while that's running, I'll just talk through what's going on. So this next step just sets up the printing. So you get like prettier printing. And then the next cell is just importing different libraries. So for this tutorial, we're going to use a mix of PyTorch, which is, I don't know, like if people have used that in the other tutorials, but it's basically just like it's like NumPy plus GPUs and different deep learning modules, basically. So we're going to use PyTorch, then Hugging Face Accelerate, which makes PyTorch easier to train with. And then, so Python has this Python regressor class that basically just, it's like, if you've ever used scikit-learn, which is this machine learning library, it's basically the exact same style of using it. Okay, so it's just compiling all these different libraries for Python. And okay, so it looks like mine is finished. So now we're going to run this cell, and this is just going to set up the printing, and it's also going to start the Julia runtime with unlimited threading, and then 3 optimized set to 3. Okay, once that's finished, we're going to import all of these libraries, and we can get to Python. Okay, so the first example we're going to try discovering with Python. So again, Python is this, it's a Python library for solving symbolic regression problems. Symbolic regression is a machine learning task where you're trying to find a symbolic expression. By the way, can people see my screen okay in the back, or should I zoom in or
Good.
Zoom in a little bit.
okay,
Zoom
zoom in a little bit.
A little more.
Okay.
Yeah.
Is that good?
Better,
Okay.
yeah. Thank you.
So the first thing we're going to do is try to learn this function. And we have to learn this function just from data. So what we're going to do here is generate a data set of 100 examples and 5 features. So it's like a table with 100 rows and 5 columns. This is just sampled from a Gaussian. And then we calculate the ground truth. So we just pass that through the equation. And this is our data set. Now, in the Python examples, we're just going to set up some default parameters. So we're going to use 30 populations for the genetic algorithm. And we're going to set up 4 processes. Okay. Now, so Python is a genetic algorithm. And just like real evolution, like it can run for arbitrarily long. Now, so basically, if you're trying to discover like a new equation, you might just want to let it run for a week and see like if it evolves a really elegant equation. But there's different stopping criteria, like ways you can kind of exit the evolution. So one of them is just setting the number of iterations. this is basically the number of kind of the number of outer loops the Peiser algorithm takes. It's roughly correlated with the number of different expressions evaluated. What we're also doing here is setting the operators. So we're saying that the binary operators, so that's operators that take in two numbers, are plus and multiplication. So this is kind of where you have to be, this is like a choice you have to make. You have to choose what operators I want to use for a particular problem. Here, we're obviously cheating a bit because we know the ground truth, and we're kind of putting those symbols into our surge. But I think that's okay. So we say you can use plus, you can use multiplication. And then for the unary operators, those are operators which take one input. We're going to say you can use cosine, exponent, or sine. Now, generally, you don't want to use both cosine and sine because it can always just like create sine from a cosine, right? Like it can just have a plus and then some phase. So it's easier for the genetic algorithm to search the fewer operators you give it, generally. You kind of want to give it the minimal set of possible operators. Okay, so now we're going to execute this cell, and this is going to start the search. Now, the first time you run Peiser, it's going to take a bit longer because it has to compile all the Julia backend. But if you're in the same Python session, the next searches will be much faster to start because then it doesn't have to compile everything. So this might take a bit, but once it starts, so actually, let me just ask, so is everybody, is everybody's code doing okay? Any issues so far?
Very smooth.
Okay.
Very
Cool,
smooth
sweet.
so far.
Okay. Oh yeah, and I should also mention, so the Colab CPUs are pretty weak. So actually, in general, you would want to run this type of search like on your laptop or on a cluster, which have better CPUs. So Colab has like really good GPUs, but the CPUs are quite weak. So this is going to be about like 10 times slower than if I was running it on my laptop. But it should still be able to find these different equations. So the first search is going to take the longest, but hopefully that finishes soon. I'll just talk through the other parts. So once that search finishes, you can basically just print. So like whenever you just enter model or like you print the model, it's going to give you this output. So this is, so it says Peiser.equations. So this is like the equations it has discovered. It gives you a bunch of columns. So there's a score column, equation column, loss column, and then complexity column. So complexity is like how complex that expression is. You see the first row is like a constant, and then you have like a really simple expression, and then it goes all the way up to whatever max complexity you set. So the next column is loss. So this depends on what loss you choose. The default is mean squared error. And it just says like, what is the mean squared error of that expression on the data? The equation column is just a string representing the equation, just for your kind of, just to review the equations it's found. The score column is a mix. So I mentioned this a bit in the slides yesterday. The score column is like a trade-off of complexity and accuracy. So it can be good to look at the score column and just see, okay, this is probably the right equation because it has the highest score. But generally, like you want to consider all columns. Like you want to consider, okay, how complex do I want this equation? If you look at the simpler equations, maybe it's more intuitive to you and you can kind of build up some understanding of the model it's trying to fit. Or if you just want like the most accurate expression, you could do that. Okay, so it looks like the search has finished. So what happens here is that it during the search, it will, every 5 seconds, it should print all the expressions that it has in what's called the Hall of Fame. So the Hall of Fame of expressions is the best expression it has seen at each complexity. So the best expression it has seen at complexity 1 is just the average of the data, because that optimizes the mean squared error. Complexity 3 is like, okay, x0 squared. And then we go up to complexity 10. So that looks like the correct expression. So cosine of x3 times some constant plus x0 squared minus 2. So that looks like the correct expression. And you can see that the score is quite high for that one. So yeah, so we can print the model and you see that, yeah, it gives us this nice output. And you can also just access that with the dot equations underscore. So this is a pandas data frame, if you've used pandas before, with all the different columns. So you can look at like the loss column, right? It gives you all the losses. You can look at the equations column, it's equation, dot equation. And that gives you all the different equations. Okay.
There's a question.
Yep.
So like from all the equipment so far, it seems like the constant is within order of 1. Is that like we need to choose like a prior for this, or like is it automatically inferred from the data itself?
You mean for the constant expression? What was the, sorry, I didn't quite catch the question.
The value seems to be within the order of 1 plus minus.
So
Oh,
the
for,
all in
wait,
America
for,
is order 1. Like if there's a prior for that, or how you.
oh, you mean in the constants, is there some prior?
Yeah. Like a range.
Oh, so yeah, so there, I mean, there kind of is, like, it should be able to find any constants that it needs to. The easiest constants for it to find are so the way it generates constants is it randomly samples from a Gaussian with variance 1. So if the constants are about 1 or like between -1 and 1, that's easiest. But actually, because it uses so it uses BFGS during the optimization, and so that means like it can just optimize directly on the constants, and it can find like constants that are like 10 to the 20 if it needs to. It's a bit more work, but it should be able to find those if it needs to. But yeah, generally, like, it is easier to normalize the data if you need to. Yeah, good question. Okay, so we can look at, so if we look at the model, there's this pick column. So there's this column called pick, and that basically says this is the equation that it is default to in the other functions. So like this is the equation that it thinks is the correct one. I mean, you could ask for a different equation, that's fine, but this is like the default. So if I do model.sympy, it's going to give me the sympy version of that row, basically. But I could ask for like a different row, like maybe I want equation 7 instead, and I just put 7 there. And it's going to give me the 7th equation. But by default, it's that one. And that one just has the best score, which is why. Yes, we can look at like other sympy expressions. If you want like LaTeX, you can get the model.latex version. And it'll just give you like a LaTeX output. Which is good, like if you need to generate like equations for a paper very quickly. I don't know. Yeah.
There's a question.
Yeah.
Nata?
Is the library internally using a train and test set? Or like
No, so the test, so it's kind of like a standard, it's so like other scikit-learn libraries, the data set that you pass it should be your training set. It does not internally do a train test split. So you should only pass it your training data, basically.
Then, I mean, but the model found the underlying true solution, why is the error not zero?
The true solution, sorry, I don't follow.
Like the model, the function that we found is the true solution that we use to calculate the data. Why is the
Yeah.
mean square not zero?
Oh, why is the mean squared error not zero? I think it's because of just numerical error. Like the precision is 32-bit, like 32-bit floats. And I think it's just like so I think we generated the data with float 64. Like this is a float this is a 64-bit number that we're doing the calculations in, and we pass it to Pyser, and Pyser does everything in 32-bit by default. We could have done, so you can change the precision with precision equals 64. That might have gotten it to 0, but like generally the constants might be like a little bit off and you might not be able to get to exactly 0. It really depends on the equation.
So the model found other expressions with a lower mean square error is just numerical precision.
Yeah, I think like, so I think that loss is just the numerical error. Like it's not that it found the wrong expression. Like this is exactly the same expression as our input, right? But it's not like, it's 10 to the negative 13, which is like, I think that's like of order the numerical error of like a 32-bit cosine.
Thank you.
Another question?
Yeah.
So one should more focus on the score instead of the law. Is that what I'm trying to say?
Sorry, can you repeat?
So whether you should focus more on the score than the loss?
Oh, you should focus on both. So you should really look at both. Like, the score is useful if there's like many equations with a similar loss. Like you look at these 4 equations at the bottom, like they're all kind of similar loss, but then you look here and like one of them is a much bigger score than the other. So that one is like the best trade-off. So the score is essentially equal to how fast the loss drops as a function of complexity. So as I go from complexity 9 to complexity 10, the loss drops from 0.01 to like 10 to the negative 13. So that is like a big drop. And that means it's going to have a big score, because this is like a metric people use in symbolic regression is how fast that drop happens. And that tells you kind of how like good the expression is. It's just a metric people use. Like it's not really, there's not really like a theoretical reason that it makes sense. It's just like an empirical metric that people find works pretty well. But you should look at like both things. And depending on the application, like you might just look at the loss, maybe, I mean, maybe you have some prior over complexities and you could kind of do some Bayesian model selection. I don't know. There's like the reason Pyser gives you the whole list of equations is so that you make that choice. Like it doesn't really, I try to emphasize like not making that choice for you, because it like it, and also for interpretability, it's actually helpful to have multiple expressions. Like this is the first order, this is the second order approximation, and so on.
Okay, there's a
Does
follow-up.
that answer?
So,
Yeah.
You can have like, for instance, at complexity 6, for instance, having a high score, but then like at complexity like 7, 8, 9, or wherever it is, you have a extremely lower loss. And then in that case, like it kind of just going more and more towards the precision, right? So by the time of 8 and 9, the score will be like so small that it doesn't matter, but at the same time, you're getting higher and higher precision, more and more complex.
Yeah, I mean, like it depends on the problem. Like the selection is not like the selection of the equation is really something that is up to the user. The score is just something that people generally use as a metric. I don't know if I fully got your question. Sorry.
Okay.
Yeah, maybe
Okay.
Claudius, you could repeat if I did.
No, it's okay.
Okay.
That's it.
Okay, cool. Yeah, so we can get like the LaTeX. There's also, like, if you really want to be lazy like me and you just want to put it in a paper, there's LaTeX table, and it just generates like the whole LaTeX table for you. You can just put that in the paper, which is really nice. Like if you're on a tight deadline, you just need the list. There's also, so there's a few others. So model.sympy I mentioned. There's also model.jax and model.pytorch. These will convert the equation into those frameworks. So if you want like a PyTorch version of this expression, you can do model.pytorch and it'll give you it. And similar for JAX. So you can use model.predict. So this is the scikit-learn standard function call. So it says like predict y from input x. By default, again, it's going to use the equation that is selected in the pick column, but you can also select a given equation. So here we have the default model.predict. It's like 0. And then the one with yeah, so this loss is exactly 0. So that kind of confirms what I thought. It's just like the 32-bit precision wasn't exactly 0. And then this is like the equation number 2. That is the predictions from that one. Like you give the index is the second argument, and that is the prediction for that. Yeah. Okay. So the next thing I want to show you is custom operators. So by default, Pyser has, so if you click that link, Pyser has a bunch of standard operators here that you can use, but you can write custom operators. And this is really what the Julia backend excels at. Like it's designed to kind of compile operators automatically. So say that we have this expression, y equals the quartic power of x0 minus 2, and say that like we happen to know that quadratic or not quadratic, quartic power is important. What we could do is define a custom power or a custom operator. So here, I write out my Pyser regressor model, and I give it plus, multiplication, cosine, exponential, sine, and then I write a custom operator. Now, this is a function that I just wrote out, and it's going to compile it and put it into the Pyser search. Now, the one thing to keep in mind is that this string you pass should be a valid Julia code. And so something weird about Julia is that you do this symbol instead of like the star. So this is like the caret instead of star. So just keep in mind, like when you're defining custom operators, they should be Julia code, which is sometimes a bit different. But you can use like any kind of Julia code you want, you can use it. Like it doesn't need to be differentiable. The only requirement is that if you get an invalid input, so say that the x is like negative and you can't take a negative number, the function should return a nan. But that's a detail, like we can talk about that later. But yeah, like you can define custom operators like this. The one thing you have to do is define it for Python as well, so that when you go to SymPy, it knows like what the hell quart is. So that's what we put here. This is like the SymPy version, is x to the power of 4. Okay, so we do the search. And it should be pretty quick now. Yeah, okay, so that was quick. And you see it found so this is like, it used our custom operator and it found that correct expression. Yeah, there is like a bit of error there. I think it's just like the gradient descent didn't quite converge. It's not a big deal. And then we can get the SymPy version. And so you see, because we define the SymPy version of that operator, it knows like how to convert it back to Python. Now, there's a few other things you could want to do. So by default, the complexity is equal to the number of operators plus the number of constants plus the number of variables in the expression. But you can kind of redefine all of these, like if you want. Like it's very up to you. So you could define complexity of operators such that court has a complexity of 2. So like we could just put that in now. So if I do complexity of operators, court is 2. You just put that in, and now it's going to do the search with that. And you see that this expression now has a complexity of 5, right? Because it's like 2, 1, 1, 1. So it's adjusted to our complexity. And so like we could have like a really high complexity maybe, and then it will maybe it'll like avoid the court. Like if I set the complexity to 10, maybe it'll just like avoid it and use multiplication instead because it's cheaper. Yeah, so you see like look at this. So it started using multiplication instead of quartic power because the complexity is like so expensive, right? Cool. Okay. Yeah. Yeah, so I say a couple other things about binary, like you can have custom binary operators too. Yeah, one thing I also didn't mention, you can also use like complex numbers if you want. That's fine. So if like you need to find like a complex expression, you can just do that too, and it'll kind of compile the operators for complex numbers. Okay, so yeah, so here I just explain like how the scoring works. So like when you have the default model selection, the default optimizes the score that I mentioned. So it's like the drop in accuracy as a function of complexity. So it's generally good when the complexity drop or the accuracy drops. Whenever you increase the complexity by a little bit, that kind of tells you it's a good expression. Okay, so here we're going to do an example with noise. I don't know why this didn't render. That's weird. This is just an N. So here we're going to sample a noise parameter sigma between 0.1 and 5. And then we're going to add Gaussian noise to our data. So here, the ground truth expression is 5 times cosine of 3.5 times x minus 1.3. And then we're going to add noise to this. And let's see like if we can still fit the expression even in the presence of noise. Now, because we know the noise parameter, like we know the noise, the scale of noise at each point, we can actually weight the data by that. So here we generate the data. We have like some sigma parameter, which is the noise scale. So let's look at the data. Yeah, so it's like pretty noisy, but there is like a pattern there that we should be able to find. So we can define weights. Now, if you have Gaussian noise, you want to use 1 over sigma squared as the signal to noise ratio. And so we can weight the loss by the Peiser search, or by the, we can weight the loss by these values. Now, by default, this will already work, but one cool thing we can do is you can write a custom loss function, and you can also write a custom loss function with weights. So you see here, I define a custom loss function as this snippet of Julia code, and this is applied to every like element, right? And I'm doing x, y, and then weight. And so that is like the weight that I pass it. And then again, I define my binary operators plus multiplication, and then a unary operator cosine. Now, when I'm fitting it, I would just do x comma y and then pass my weights. Weights equals weights. But yeah, like I think the custom loss is very useful because a lot of times you want to use like a log likelihood there instead of just mean squared error. So you could write like any function here. Again, it doesn't need to be differentiable. You can just pass it in. Okay, let's start that search. And it's going to optimize with the weights according to our custom loss function. Okay. So it's not like as quick as the other ones because there's a lot of noise in the data, but it does seem like it kind of has it there. Yeah, so that looks like it's correct. Okay, so like once it's finished, we can plot it. So you can see it tells you the expressions evaluated per second. So on my laptop, I can get like 10 to the 5, almost 10 to the 6. So you can see like it's pretty slow on Colab. I mean, like it still works, but it's going to be faster on your laptop. Okay. Almost done. Any questions?
Look good.
So I think, yeah, I think like what we're seeing here, the first few expressions are like all of these expressions are kind of the same loss, right? This one is kind of the same as this one. So I think it's just like overfitting to the noise a bit. And this is another place where the score column becomes useful because you see like this first row has a really good score and then the score kind of drops off in the next ones. And I think that's just because like there's just not enough gain per complexity. So it's just kind of like overfitting to the data. So let's see the model. And I think, yeah, I think this is the right equation. Yeah. I think it's like a little bit different just from the noise, but it's pretty good. Yeah, so we could look at the SymPy representation. Well, that's SymPy. Yeah, so I think that, what did we put in? I think that's what we put in. Yeah, 5 cosine. Yeah, that's correct. Yeah, okay, cool. So the nice thing about the equations being a pandas data frame is you can use like all the pandas data filtering stuff. So like if you want to look at the equations with, I don't know, some loss, you could just look at that subset of the equations, or like the equations with some, I don't know, like some score threshold. This is kind of like a minor detail. We don't need to look at it. But like if you want to kind of filter the equations in a different way, you could do that. Okay, so now that we have our equation, we can look at the fit. Oops, I'm actually supposed to run this. Okay. Yeah, so that's a nice fit. So what we did there is we said model.predict, and we used the best index that we calculated. I mean, we could also just delete that. It's going to be the same because like the default is already looking at the trade-off. But yeah, like you can fit in the presence of noise. You don't have to use the weights. Like we did use the weights there just because we knew the signal to noise of each point, but you don't have to do that generally. It should be okay. The nice part about symbolic regression is it's bad. It doesn't really overfit. Like you could have 100 data points and it's still like reasonably robust because it's just symbolic regression is just not really expressive enough to kind of fit anything. Yeah. Question? Is there a question? No? Okay. Okay. So you can also fit multiple outputs. For multiple outputs, it's just going to fit like a different equation for each output. There isn't like I think eventually it would be cool if there was like a vector symbolic regression. But right now it's just It's just like different equations. I mean, you could kind of look at the different equations and see like, oh, they're kind of different vector components. But there isn't like a separate vector search. Okay, cool. So here we're looking at this vector equation where it is 1 divided by x0 or x1 for the second component or x2 for the third component. Okay. And you would just like call this normally. So model.fit with a matrix and it'll work the same. Here we've also defined a custom operator to kind of cheat. And so we define this custom operator called inv, which is just like the inverse. And so it's going to search with that. For multiple, when you're searching with multiple outputs, it'll just give you like 3 lists, right? So these are the best equations for output 1, best equations for output 2, and output 3. And so you see it finds the correct one in each. So inverse x0, inverse x1, inverse x2. Cool. Okay. I think it's done. Is it? Almost done. Okay. So we can look at the model. And it's, so now instead of being a single data frame, it's 3 data frames. So we have 3 outputs. So we could look at the SymPy and it's going to be 3 equations. So I don't know why it found like this constant. Sometimes like you have to kind of train it a bit longer to kind of smooth out all the other stuff it might learn, but yeah, I think it's fine. Cool. Okay. Yeah, any questions or anything people want to ask about or like use cases I'm happy to talk about. Yeah, is everybody's like code working okay?
There's a question.
Yeah. Claudius, can you repeat it?
Yes, there were getting an uncertainty on this.
Oh, you mean on the equations?
Yeah, on the constant.
On the constants.
Oh, on the constants. No, not by default. But like part of the issue is there's not really a good way of defining priors in symbolic regression because the probability of the equation like x multiplied by a constant is the same as x divided by a constant. So like whatever you define over constants is going to actually result in like weird priors depending on the equation you find. So actually by default, there's not like any prior over constants. There's not really a way of getting uncertainties. One thing some people do is when you get these equations back, you could look at the, like you could kind of re-optimize it and just like refit the equations with a Bayesian like MCMC framework or something. That is an option, but there's not really a good way. Like there are some ideas for kind of marginalizing the space of equations, but it's really tricky to do that. So it's much better to have like a single equation and maybe do like uncertainty calculation manually.
Okay, thanks.
Cool.
Another
Okay.
question?
What would be your recommendation on how much data should, like every time I'm trying a new function, I'm calculating the loss of my entire data set, right? So if I use 1 million data points, it's going to become very, very slow. So was the right intuition, more data is not necessarily helpful here?
Claudius, can you repeat it?
Yeah, question was about the data set size. So if you have a bigger data set, is that beneficial or is it just getting slow? Or
Yeah. Oh yeah, that's a good question. So yeah, like generally you can get away with like 1,000 data points and you can fit like really complex expressions with 1,000 data points. I mean, it kind of depends on how much noise you have. You need more data if you have a lot of noise. But yeah, it's going to be slower. So like if you have 10 times as much data that you're feeding in, it's going to be 10 times slower to search. So one thing you might want to do is randomly like subsample the data set before giving it to Pyser. There's even like a warning that will come up when you try to give it more than 10,000 data points. It's like, it'll be much slower, blah, blah, blah. So you might want to like randomly subsample. Because it is much slower to search with a lot of data, and you really don't need it, I guess. Yeah, the case like where you might need it is if you have a lot of noise and it needs like all the data points to kind of accurately gauge whether some expression is the truth. Okay.
Okay, thanks.
Cool.
Oh, yeah, another question.
So what would be like a suitable complexity to which you can go to like with the proper simulation time,
What's a suitable choice for the complexity?
like the maximum complexity that will
Like the maximum complexity?
like it is very like quite high, especially with quite high complexity, right?
Yeah, it's gonna like, again, it's gonna kind of depend on the problem, and it is really like up to you. So if you're using PySer for interpretability, that is like the max complexity is completely up to you, and like how complex you want the expression. Generally, it's a good idea to set the max complexity, which is, it's actually called max size. That is the parameter. Like model.max size. Generally, so the default's 20. Generally, you want to set that a little bit higher than the max complexity you were kind of looking for. Because it gives the genetic algorithm a bit more room to work and kind of explore the space. So you want to go a bit higher than kind of what you're looking for. But it really depends on the problem. Like sometimes I've used really like high complexities, like even up to 100. For that level of complexity, you really need like a lot of compute to kind of fully explore that space. Generally, I only go up to like complexity 30. And that's of course with default complexity settings. Like if you start redefining the complexities of operators, you might set that higher or lower. Yeah.
Another question?
Can we also set a minimum value for complexity?
So is there also a way to set a minimal complexity?
Oh, no. There's no minimum complexity. I think minimum complexity, you would just like filter them in the output. Yeah. I don't know if that would like, yeah, I mean, I'm open to adding that if that's something you think would be useful. I'm trying to think like if that would help the search at all, if there's a minimum complexity. I'm not sure. Yeah, but yeah, that's interesting.
You know, beforehand that the problem is not so easy. You in a complexity one.
Yeah, that's a good point. Like, I don't know, but at the same time, like it can use the simple expressions to bootstrap the more complex expressions. So like it can use like a cosine x0, it can kind of like do a crossover and put that into a more complex expression. So the simple expressions is not so much just assuming that you want to view those. It's kind of so the search can use those to explore the space, I guess. That's kind of the intuition behind it.
Okay, thanks. There's one more question.
Is there any way for the algorithm to have some built-in simplifications? Like if you have x plus x perfectly turned into 2x?
Yeah, great question. So there's only 2 simplifications right now. So if you use the plus operator and the multiplication operator, I think it's like there's some simplification strategies dealing with plus, minus, multiplication. They're not extensive. Like it's like really simple things. Like if you have x plus a constant minus a constant or plus another constant, it'll just like combine the constants. It could be interesting. So there is a algebraic, like a full algebraic simplification package in Julia, and it might be interesting to try like exploring integration with that. One of the issues that one has to worry about is if you simplify like too often, it'll kind of over trim or over prune your search space. So like maybe you actually want to go to x0 minus a constant plus a constant, because from there it can kind of jump to a different expression. So if you simplify like too much and too eagerly, it will kind of prevent exploration. So like you kind of want to treat the simplification like another random perturbation. But yeah, it is like a really interesting direction. Part of the difficulty there is if you have like user-defined operators, you would need to kind of ask the user for, I don't know, additional simplification strategies. Like, okay, what are some algebraic rules of your custom operators? But I think that would be really interesting to try adding. Yeah. Another thing I should mention is it can kind of simplify automatically because it is jointly optimizing the complexity and the loss. So it's going to naturally tend to simpler expressions. But yeah, I think like a real algebraic simplification would probably help. Yeah.
Thank you.
Yeah, just follow up from my side. Can't you run this on the final outcome, like not during your optimization, but before you print out the leaderboard?
Yeah,
So then
totally.
you would not mess up the optimization.
Yeah, so actually, so if you do, like if I look at the SymPy expression, so SymPy has a simplification. So I think it's dot simplify. I mean, that one's already simplified, but you could do that at the SymPy end. Definitely, yeah.
Okay, thanks.
Cool, okay. Yeah, so one thing you could also do is, because you can have arbitrary operators in the search space, you can actually think about like combining other Julia computing packages, like as an operator. So in this example, say we want to learn this expression. So this is a bit of a crazy example. We want to learn y is equal to the ith prime number where I is equal to 3x plus 1. Okay, so this is like a bit crazy, but let's see if we can find it. -5. Now, to do this, we are going to install the primes.jl package, which kind of has a list of prime numbers. So we get the Julia backend. So this is JL. We put it in the variable JL. So JL is the Julia runtime. And then with JL, we can evaluate Julia expressions. So in Julia, you add a package with package.add. So this is the equivalent of like pip install. And we're going to add the primes number package. So you import package, package.add primes. And this is going to install the primes number package. So once that installs, we can import the primes number package. And I think like the use case here is that you might have, like maybe there's some, I don't know, some, like I remember someone was asking about like dilogarithms, like could you use a dilogarithm as an operator for like particle physics? And you could add the dilogarithm, I forget the name of there's like some package that does dilogarithms. So you can think about like adding that package and then using that as an operator. So here we're just doing prime numbers. So we do import primes. And then we can define a custom operator. So this is like defining a function in Julia. I don't want to give like a full Julia lesson. So you could just like, trust me, this is the ith prime number. And we're just defining a custom function. It basically says, if I is between 0.5 and 1,000, return the prime number that is closest to that number. So if it is like 0.6, it's going to return the first prime number. If it's like 2.3, it's going to return the second prime number, right? If it is greater than 1,000, it's going to throw a nan. So it's going to return a nan number. And that basically says, it says to Pyser, like, this expression is invalid. So set the loss to infinity or whatever. So that is so we've defined this custom function. I don't want to give too much on the Julia side, but basically, like, we're going to generate a data set of prime numbers. And here we go. So so this is our input data set. It's just like a bunch of integers. And then our output data set is the 3x plus 1 prime minus 5. And then we're going to add a bit of noise to kind of mess with it. Let's see if Pyser can handle like a little bit of noise. Okay, so it should be able to, just from like this list of X and Y, hopefully it should be able to find this like prime number relation. Like it should map 12 to 152, 1 to 2, using this prime number operator, hopefully. Okay. Okay, so we define a Pyser regressor. We've already created this function called P, which is like the prime number at I. So we're going to just pass that to Pyser, and it knows that that is like a Julia function. And we're also going to say to SymPy, because I think SymPy, I don't know if they have a prime number mapping. So we're just going to leave it symbolic. So we're going to say there's some symbolic operator called SymPy P. Okay. So we've now defined this Pyser search with our custom operator, and let's fit. Now, this is going to take a bit longer because prime numbers, I think the prime number package is like, I don't think it stores the prime numbers. I think like every single time you evaluate, it's like actually calculating the prime number with like a prime number sieve or something. So it might take a bit longer. Okay, I think it already found it. That's cool. Okay. Yeah, so you see it's like 3x minus, or it's plus, I guess it's plus 1. What was our equation? Yeah, 3x plus 1, find the prime number, and then minus 5. So it looks like that. So I think the fact that that number is not exactly 1 is just because we have that rounding. So it actually doesn't matter like where that constant is, because it's going to round to the nearest integer. So that is like approximately 1. Yeah, so it found it. So that's cool. This search is going to take a while because I set the iterations kind of big. So we could just talk about the other stuff. Are there any questions on this? Because I think I went a bit fast through this part. Questions?
I don't see any hands, but I see people nodding, so I think you're good.
Okay, cool. Okay, so yeah, it's still searching, but it already found it. So yeah, so when we do model.sympy, it's going to write this. So we've kind of like defined this symbolic operator, and it's not going to evaluate. It's going to look something like this, which is true. So it found the correct expression, even though it's like this very non-differentiable, complex function, it still found the correct expression, which is cool. So you could think about like how to use this in different scientific examples. Okay, so yeah, so we'll just let that finish in the background. Now this next part, oh yeah, so I'll just stop here maybe and ask like if there's any questions on Pyser itself, because the next part is going to be using Pyser to interpret a neural network. So it's like, it's a bit different. Any questions? And I could also point you to the API page. So if you go to the PySer docs, there is the PySer regressor reference, and this is all of the options that you have. So you have like the binary operators, unary operators, max size, max depth. There's too many options, to be honest. And you can see like on the right-hand side, there's categorization. So you could click like creating the search space. You click on that and it goes to the different options. Maybe you want to go to the mutation settings. So like, how do I define different like weightings for the mutations? The defaults are pretty good there. You could think about overriding them sometimes. There's stopping criteria. You could think about like limiting the number of evaluations. You can have timeout in seconds. If you don't want it to run like more than 1 hour, you could set that. Yeah, I mean, there's too many options, to be honest. But yeah, I try to like categorize them so it's less daunting, I guess. Any questions?
Just see there the defaults for the binary operations plus minus.
Mhm.
Isn't that redundant?
Yeah,
Plus
yeah.
before and found negative constants. So is there any
Yeah, so it
using both?
kind of is because but it's actually more expensive to do plus and then multiplication with a negative number. So if the true equation is like say it's like x minus y, that is complexity 3. But if you did that with plus and multiplication, it would be x plus -1 times y, which is complexity 5, I guess. So it also helps for the simplification if you have both. But it is true, like you could represent that just with plus and multiplication.
Okay, no, I was thinking about the constants, but you're right. When you combine functions, then it's different.
Yeah.
Okay, thanks.
Oh yeah, and I'll also mention, so if you go to the performance and parallelization section, so this is where you would go if you have if you want to like run this on a cluster or something. So there's a cluster manager section. And this is where if you have like a Slurm cluster or like a PBS cluster, you could just pass that and define the number of processes over all nodes. And it hopefully, so I think you have to do, you set the processes, you turn off multi-threading, so it switches to multi-processing instead, and then you set the cluster manager. And it should be able to kind of like batch out and distribute populations to the cores. It's only been tested on Slurm and PBS. The other ones use the exact same cluster manager API, so they hopefully should work, but please let me know if they give you any issues. I think like when you're searching for much more complex expressions, it can really help if you give it like just a shit ton of compute. It can like really help the search. Because it's kind of like evolution, like you have like a lot of species or a lot of like individuals evolving in a species, like they can kind of evolve faster. So it can help a lot. Oh yeah, okay, so I think it finished searching. Okay, cool. Yeah, so this is correct. Any questions on other stuff? Okay. Cool. Okay, so the next thing we'll do is, so this is the neural net symbolic, so we call it symbolic distillation. So you have a black box neural network model and you try to interpret it with symbolic regression. So we're going to set up a toy problem here. It's a time series problem. We have a time series let me just write, so we have X, I, T. So this is our time series, right? So we have X, I, T. I is the, or shit, wait, it is TI, sorry. So we have a time series of vectors. So at a given time step T, we have a vector that is like some dimensionality. Now, the summary statistic of this time series is given by Z. So Z equals Y squared, where Y is the sum of the time series. That is kind of like our summary statistic of the time series. Okay, now the yi is equal to some symbolic expression of the xti. So basically the expanded expression is actually quite complex. So it's equal to the square of this quantity, where this quantity is equal to this. So it's a bit like, it's a bit more complex of an expression. Like we have a different axis. So rather than just vectors mapping to scalars, now it's like a whole time series mapping to a scalar. Any questions on this? Because I feel like this part's kind of confusing. Okay. So basically we want to map from this time series to Z, to Z. Now, the way we do this is we would have some neural network. So maybe we have some neural network that gets the instantaneous, I guess like vector. So say there's a vector at some time step I, and we have one neural network that kind of maps from that vector to some scalar quantity. We then sum over the time series, and then we take that sum and we map it through a different vector, or through a different neural network, sorry. So it's this two-part neural network that is going to try to map from a time series to some summary statistic. And we have the ground truth summary statistic in the original time series. And first, we're going to just train a neural network to map that relation. Okay. Any questions on this?
Yeah, there's one.
Yeah.
I'm actually confused. This I index is the time index, right? In the equation. Why?
Claudius, can you repeat
The
it?
question was whether the I index is the time index in the equation.
Yeah. Oh, yeah.
What are the-
Sorry, I'm so bad at indices. I'm just going to call this I, sorry. Yeah. So I is like the time index. Yeah. And when I write xi, I just mean like all the j's at that step. Does that help?
Yeah, thanks.
So xi0 is like the 0th feature at that time, and xi2 is the second feature at that time. And so we want to estimate this entire hierarchical equation from just x and z. Okay. Okay, cool. So first thing we're going to do, we're going to generate that data set. So let's give it 100,000 examples. Okay, 100,000 different time series. The number of time steps is 100. And we have 5 features. So at every time step, there's 5 features. And we have 100 time steps and then 100,000 examples. So that's our data set. And we map it through that expression I wrote above. So it's x0 at each time step squared plus 6 times the cosine of 2 times x2. Okay. Actually, I think I'll modify this. And I'm actually going to make this 10 time steps rather than 100. Because I'm looking at it now and I'm like, oh my God, the cosines are all going to cancel each other out. Because you're summing like a bunch of cosines. So I think 10 time steps is actually better. Okay, so if everybody could like modify their notebook to make it 10 instead of 100, I think that'd be better. Okay, so we're going to generate the data set. So now we have 100,000 examples, and we're going to try to map from X to Y with a neural network. Oops. So now we're going to define our neural network model. Okay. Now I described it above. We're gonna define 2 neural networks. One neural network called G and one neural network called F. Okay. So what I'm doing here, I'm defining a multi-layer perceptron, just like some neural network that can fit vector-to-vector mappings. And I'm using that to define G and F. So G is the first neural network. It's going to map from the 5-dimensional vectors to a scalar. And F is going to take the summed G and map to Z, like the estimate of Z. Okay. So this is the same. This is like Z equals F of sum of G of X, I, right? So that's what we want to, that's what we're basically defining as our model. Okay. The forward pass is given here. This is basically the PyTorch version of this. So like this comment, Z equals F sum of G, is just equal to this. Like this is the code version of that. Okay. So that's the sum. That is applying G to every time step. And then we're taking the summed version of yi and then mapping it to Z. Okay. So for the loss, we're going to use mean squared error loss, just from the predicted summary statistic to the true summary statistic, right? So we give our model X and it returns a prediction for Z. Okay, this other code here is just like configuring the optimizer for the neural network. This, like, none of this is kind of PyTorch, or none of this is PySer specific. This is just like regular neural network stuff. Then what we're going to do, we're just going to put everything in our data loader for PyTorch. Again, this is just like PyTorch boilerplate. Okay. And we're going to create the model. Let's train it for 50,000 steps and create the optimizer. Now, to use the GPU, we're going to let the accelerate. So this is, I mentioned this package. It's called Hugging Face Accelerate. It's this like really nice PyTorch helper library. It basically just moves stuff on and off the GPU automatically. This is just like neural network stuff. Okay, so it's going to put everything on the GPU for us, and then we can start the training. Okay, and so we start the training. Let's see. So it's going to go through the training step, and here we go. So this is the loss of the predicted summary statistic from our neural network compared to the true summary statistic we calculated above. Okay. Any questions on this so far while we wait for it to train? yeah, the loss is going down. And yeah. So what I'm showing here is the step number, which we're going up to 50,000. And then this is the median of the last 50 losses. So the last 50 mean squared error values. And again, this is just like regular, I guess, neural network training. The important step is after we're going to try to interpret it with PySer. Or any issues like anybody's experiencing with the notebook at all? Sometimes like PyTorch and PySer, they have like a fight and they'll like fight over the C library. Or there's like some C library it has to load and it's like, I don't know, the pointers get confused about who owns it or something and it'll like crash, but this one seems fine. Yeah, it's the tricky part about Python is like all these libraries have different backends and the backends are trying to like load different C libraries, I guess. So if you do have issues with like PyTorch and PySer interfering, you could just like run PyTorch, save the model, and then load PySer in a new session and kind of like interpret the model there. But it seems like it's fine so far. Okay. Was there a question? Sorry.
Looking good.
Okay. Yeah, I don't know. Has anybody used like Hugging Face libraries before?
I see people only shaking their heads.
Oh, okay. Yeah, it's really nice because it like you don't have to transfer stuff to the GPU. You just like, you literally just like put everything through this command, accelerate.prepare, and it just like, it kind of like automatically moves stuff on and off for you, which is really nice. And it can even handle like multi-GPU, multi-node stuff. So it's really good for like distributed training of neural networks. Okay, so loss is getting pretty good now. It's like 0.01. Yeah, I think so. I might have like a better GPU than other people. I don't know because I pay like this pro because Google doesn't give me it for free, which they should because I'm like advertising it. Yeah. But so I might have like a better GPU than others. I don't know. So I don't know how far along your training is. Okay, almost done. Yeah, neural network training is it's hard for like impatient people like me because like I always want to stop it early and like look at it, but it's important to be to wait for it. Okay. Almost done. Yeah, so the loss is pretty good. Okay, so mine finished. So I'm going to walk through the interpretation. Basically, we have this model that has now been trained to do that relationship of like taking X at some time step, mapping it to a scalar, summing that scalar, and then mapping it through a different neural network, right? Like we have that model trained. So now what we're going to do is take our data, which here we've called it X for PySer, and we're going to put that data through the neural network. Okay, so we have this neural network G. We are going to, I'm going to just comment out this other stuff to not confuse you. We're going to take that neural network's output and we're going to try to fit it with PySer. So this is the input to the first neural network and the output of the first neural network, right? So we have this, I think this is right. Yeah. Is this right? Let me see. Oh, wait, sorry. So I think let me see. I think this line actually looks at the wrong index. So it should be 0 here. Or no, it's right, sorry. Yeah, ignore me, I'm being dumb. Okay, so this is correct. Yeah, so we have like the input to the neural network and the output of the neural network. So now we're just going to fit that with PySer. Okay, so what we're doing here is we're moving it to NumPy and just like flattening the array. And we're going to randomly subsample 3,000 data points. Like we don't need all that data, so we'll just sample 3,000 data points. In PySer, we're going to give it like plus, minus, multiplication. And so we're kind of cheating, but we want to like finish this on time. So it's like cosine, square, negative. I mean, I guess like we don't really need the negative, so we could delete that. Okay, let's fit. So again, we're fitting the inputs and outputs of one of the neural networks in our model. Okay. So it's going to do the search. Okay. Yeah, so it looks like it's kind of finding it, which is cool. Yeah, are people like having any issues? I can't see, so just like let me know if anybody's having issues. Seems to do okay. So sometimes PySer will have these like square of a constant. It's generally appears just to like numerical precision issues. But it's fine. Like when you do the post simplification in SymPy, it'll just go away. So it's not a big deal. Okay, so let's see what the model gets. So remember, we're searching for this hierarchical symbolic expression. The network we're fitting is the network that has hopefully learned this expression. So if we're successful, we should find this from PySer. So let's see what we got. It's too long. Let me do model.sympy. Let's see what we get. Is that right? Okay, we have x0 squared plus 10 times cosine of 2. Okay, so this is actually correct. So we've been about as like successful as possible. The reason there are extra constants on this expression is literally because neural networks are so expressive. The network for F, like the second network, is just undoing this linear transformation. So the first network has not learned exactly this. It's actually learned this expression times 1.6 minus a constant. And then F is just like undoing that. So it's actually correct. Like the first network has learned the truth plus some constants. So it's actually correct. So that's good. Like we found the neural network has learned the correct model, and now we've kind of recovered it with PySer, which is cool. So we could do, like, we could also fit the first F, and it would hopefully contain the inverse of those expressions. I mean, we don't have to do that now, but like you could do that. Any questions about this?
There's a question.
So how reliable is this result? Because I got a very different result.
So how reliable is the result? Because he got a different result in his run.
So how different is it? Is it like wrong, or is it just like a different constant?
it's very different. It's cos square is there, and then the factor is like 26.
It's very different. So there's a cosine squared.
And also, what is the how many times we are running? Because I think it's like
Okay, there's too many questions at once. So there's a few people here that said they got cosine squared in their results.
Do they have, so you might want to like look at the other expressions because it could be that it has like found it, but it just like didn't select it from the list and it like selected the cosine squared. Okay, so like some of my expressions are like x0 squared times cosine squared, but it does contain the correct expression. So like sometimes you kind of have to look at the full list. If the full list, like if it doesn't contain the correct expression, then it could just be like the neural network needed to be trained longer. I mean, we're only training the network for like 50,000 steps. Usually you want to train neural networks. If you want to make them converge, you have to train them like 1,000,000 steps. So it could just be like it had a bad initialization and mine happened to converge faster. Like the network could have like learned that with the time it had, I guess, is what I'm saying. The other thing, oh, sorry.
Question. So yeah,
So does it depend on the number of times?
so does it depend on the number of times they're running the same code?
Yeah, so like if I reran this exact same code, I would get a different scaling. And that's just because like every time you initialize the network, you're going to start at a different point and it'll like find a slightly different model because the second network is just going to invert that. So there's like a gauge freedom here. And the network just picks some gauge, basically. And that's what we're seeing in these constants. It's like that is a degeneracy in the model space that the network has just like picked some point in that space. So like this constant is completely arbitrary, so long as that if I divide the whole expression by that constant, it should recover this plus another constant. So it's like the same, yeah, I guess it's the same degeneracy that Lagrangians have, like the same freedom, the same symmetry. Like you can multiply them by any number, add any number, and it's still the same dynamics. So it's the same kind of symmetry here. So you randomly initialize the network, you'll get like a different scaling, but it's still the same model. So like if we did do the symbolic regression on the network for F, it should hopefully have the cancellation, so that if we stuck those two equations together, it should hopefully like always be the exact same thing. Plus like there's going to be like some noise, whatever. But like if you have both equations, you compose them, it should be the same. Hopefully.
There's one more question.
So is there a way of restricting the use of two operating together? For instance, I don't want cos square, but then a way of like preventing it from going towards any form of cos square.
Yeah.
Is there
Yeah, great question.
blacklisting?
Yes. So great question. So if you look at the Peiser regressor reference, you can go to the working with complexity section here. And there's this thing called nested constraints. It specifies how many times certain operators can be nested. So what can happen is sometimes like you can just have like cosine of cosine of cosine. You can disable, like you can restrict that. So in this search, maybe I would say, so let me do a search for 1,000 subsample, and I'll say that I don't want square to ever contain cosine. So I could write nested constraints equals square is never going to contain cosine, so 0. So it can never contain a cosine. And then if I run the search again, it's never going to find that kind of expression. I mean, we're cheating a bit here because we like know that, but it can be good, like if it's finding tons of uninterpretable expressions. It's really good for power laws because I didn't know this, but like you can have nested power laws, like to the power of, to the power of, to the power of, and you can fit like tons of things. And I didn't know that until like Peiser started doing that. You can get like really good fits, but it's like, it's so uninterpretable. So you can just like disable that. So yes, you see here, like none of the expressions have square of cosine. There's cosine square, but no square of cosine. Yeah, so I kind of disabled it, which is cool.
Okay, thanks.
Okay, so I think we're at the end. So I'll stop there. The last part of this notebook, which you could do if you want, is about inductive biases. So it's like Hamiltonian neural network, different invariances. But I will conclude there. Yeah, so thanks for coming. Sorry again, I couldn't make it to Germany. I wish I had been there, but yeah, thanks for having me and attending.
Yeah, thanks for a great lecture.
Yeah.
Any other questions? If not, thank you, Miles, and we keep in touch.
Great. Okay.
Perfect.
Yeah,
you.
thanks everyone.
Bye.
Bye.
My background was blurred. I didn't realize. I had Zoom with background blur. Like, you know, when you start a video and your background is blurred.
But I thought he saw what is going on.
I don't know. I hope